Now it's time to talk about the intermediate value theorem, and what I'm going to do is explain the theorem and draw a graph and explain the idea to you, and then I'll state the theorem, I'll write it out, and you can write it into your notes. I'm not going to prove the theorem, because once I state it and explain it, I think it should be obvious to you. But then I'll also work through some examples and show you how it can be used and why it is significant. Okay, here we go. Let's imagine we have some function like this. You can draw this in here. It could be any curve, but let's say it's some x value, we'll call it a. The function has a value, obviously, f of a. And at some x value over here, we'll call it b. The function has a value which is obviously going to be f of b. Okay, if this function is continuous over this interval, a to b, that means if you can go from your x values all the way from a to b and never leave the paper with your pen, there's no breaks or discontinuities anywhere in this function. If it's continuous over a and b, or over the interval from a to b, and we have some number between f of a and f of b, I'm going to put it here and call it y. So there's some y value between f of a and f of b. Then there must be some point on the curve that corresponds to a point down here. We'll call it c. There must be some number c in this interval such that f of c is equal to y. Another way to say it is that when you go from a to b and you move along this curve, then you're going on your y-axis from values f of a to f of b, then you have to go through every y value in between. So if there's some y value between these two numbers, there must be a point on the curve with an x value such that the value of the function at that x value is that y value. And you'll find that point somewhere in this interval. Okay, now let's state it formally. We could say it like this. If function f is continuous over the closed interval ab, so in your notes you can write this. If f is continuous over this interval a comma b with the square brackets, and y is a number between f of a and f of b, and y is a number between f of a and f of b, then there is some number c in this interval in the interval AB, such that f of c is equal to y. Okay, that's the intermediate value theorem stated in general terms. If we go along this curve, and in doing so takes us from this y value up here to this y value, then we have to go through all the y values in between. And if you have some point y between these two y values, then there must be some point x in this interval such that f of x, or we called it c in this case, must be some x value, call it c, in this interval such that f of c is equal to y. And here's an example. Suppose that f of x is equal to x squared, and we're asked to show that there is a number c between 2 and 3 such that f of c is equal to 7. And let's draw this. Let's picture this visually. Here's our graph, and we know what the x squared graph looks like. It's a parabola. let's plot a few points here. Let's make the point a 9 and 3, and we'll plot 1 and 2. 2, 4 is on the curve, and that's good. So now imagine this interval, between 2 and 3, some x value between 2 and 3. So we're dealing with this interval here. So imagine moving along the curve from this point to this point. Well, in doing so, if your x values go from 2 to 3, then your y values go from 4 to 9. So the intermediate value theorem says they have to go through all the intermediate values between 4 and 9. So the number 7 is in fact between 4 and 9. So the intermediate value theorem says there must be a point on the curve here and some x value down here such that f of x, or we typically call it c, some x value c such that f of c is equal to 7. So if you wanted to show this, you would write for your answer, you would say this. You would say f of 2 is equal to 4 and f of 3 is equal to 9, and f of x is a polynomial even though it's a very simple polynomial, it's still a polynomial and is therefore continuous. The intermediate value theorem only applies to continuous functions. So f of x is a polynomial and is therefore continuous. So it must be continuous over this interval because it's continuous everywhere. And it's therefore continuous, so the intermediate value theorem applies. And then I would say that 7 is between 4 and 9. So there must be some number c between 2 and 3. I'm talking about some number right down here between 2 and 3 such that f of c is equal to 7. And that number would be, we can say what it is, it would be the square root of 7. Now, one interesting side note is one of the things that we've shown here is that the square root of 7 exists. The square root of 7 is an irrational number, and we've just shown that an irrational number exists, and that's actually significant. The existence of irrational numbers was not always accepted, particularly in the early years of mathematics. I'm going to go down a little side road here because I think this is really interesting. The Pythagoreans, obviously, under the leadership of Pythagoras, developed a lot of significant mathematical theory. You're familiar with the Pythagorean Theorem, no doubt. Pythagoras also did a lot of other stuff. The physics involving music and chords and ratios and how certain notes combine to make pleasing chords. They developed understanding of the regular polyhedra, which they kept very secret. And this secrecy of the Pythagoreans was a big deal. Let me get a picture here. This is Pythagoras. This is a picture from Raphael's painting, The School of Athens. And you see the people adoring Pythagoras. Pythagoras was greatly revered in the culture, and his inner circle of followers were greatly revered. And they were the leaders, the political and religious leaders of the culture at the time. And they had this view of the world that was based on number. Musical chords fit together in perfect numbers. There's certain perfection in the heavenly bodies according to perfect numbers. And their whole view of the world was based on number. And that was a big deal. And the Greeks discovered the existence of irrational numbers geometrically. You could take a triangle, for example, and you could build this. Say this is length 1, this is a right triangle, and this is length 2. Well, what's the length of the hypotenuse here? Well, with a Pythagorean theorem, we can say the length of the hypotenuse there is the square root of 1 squared plus 2 squared, which is the square root of 5. And you can actually draw this. This length must be the square root of 5. You could construct it, but you can't write that number. It's, what would that be, 2.236? But these digits go on forever. You can't write this number. It's a number, and numbers were important to the Pythagoreans. It's a number that you can actually draw. It must exist, but you can't actually write it. And they were afraid that irrational numbers undermined their system of thought that was based on number. And they were afraid that it would undermine their power in the culture, politically and spiritually. And so they actually had a law against talking about irrational numbers. And everyone in their inner circle was forbidden to discuss irrational numbers. And they actually had the death penalty. And there was a guy, it was Hippasus. Hippasus was executed by drowning for discussing irrational numbers in public. So fortunately, things are different today. But what we've shown here in this example is that the square root of 7 exists. There is a number between 2 and 3 such that f of c equals 7. So it must exist. So aside from using the intermediate value theorem, and it can be used in other ways as well, we've used it here to show that an irrational number really does exist. It is a real number. And we'll see some other uses of the intermediate value theorem coming up.